Our next example, right? This is adapted from the Society of Actuaries exam. You're told that X is boson with mean rate lambda 1, Y is boson with mean rate lambda 2, X and Y are independent. You're told the first moment of X is less than the first moment of Y by 8. Okay, what does that mean? You're told that the expected value of Y minus the expected value of X is equals to 8. Okay, that's what it means. Yeah, the first moment of X is less than the first moment of Y by 8. So which means if you call this lambda 2, so it'll be lambda 2 minus lambda 1 equals to 8. So there you have it, right? The second moment of X, yeah, is 60% of the second moment of Y. Yeah, the second moment of X is 60% of the second moment of Y. So we are saying that the second moments, right, of X is 0.6 second moments of Y. Okay, good. So we know that variance of X is expected value of X squared plus expected value of X whole thing squared, correct? So this will be what? Lambda 1 equals to expected value of X squared minus lambda 1 squared. So the expected value of X squared will be lambda 1 plus lambda 1 squared. That's what you see here. Okay. So that means the expected value of Y squared will be what? Good. Lambda 2 plus lambda 2 squared. But don't forget, it's 60%, so there's a 0.6. So we have two equations and two unknowns. We can easily solve this. Okay. This is an easy system to solve, and you can get your answer. Okay. The answer given in the book. Remember what have I written here? The original question wanted lambda 2. Okay, so go ahead and work it out and see whether everything fits in. Okay, good. Let's do one last example here in this chapter. We want to talk about mixed distribution a little bit in this example. Remember I said I was going to talk about using the normal approximation for the Poisson distribution as well, but never mind. That one we'll do it next time, okay? Not such a big deal. Okay, the ideas are the same as how we did it using how we approximated the binomial probabilities using normal distribution. So now, man, let's move on, right? So this one example here, let's read the question. A random number generator was designed such that it had a 10% chance of producing an integer value of 0 or 1. Okay, careful, right? A random number generator was designed such that it had a 10% chance of producing an integer value of 0 or 1. If so, excuse me. If so, 0 and 1 were equally likely to appear. So probability of 0, okay, probability of 1, okay, 0.5, 0.5. Otherwise, it generated a number between 0 and 1 with the following probability density function. Oh, okay. Or X values between 0 and 1. Okay, good. So, find the variance of the generated number. Okay, so what you need to do in a situation like this is to read the question, maybe read it a couple of times, right? See what is the information they've given us and see what they want us to find. Okay, so because they tell you that there's a 10% chance of producing a number between, 10% chance of producing an integer value of 0, 1. Now, if so, 0 and 1 will be equally likely. So then you must know, then the probability of 0 will be 0.5. The probability of 1 will be 0.5. Equally likely, right? Otherwise, yeah, okay, it generated a number between 0 and 1 with some density function. And you asked to find the variance. Okay, so just to remind you, actually I don't have to because I think you are pretty good at this by now. Okay. Okay. We know this formula really well. So this solution is kind of brief. So you can expand on it, right? The idea was for me to actually give you some hints, but never mind, yeah? So this part here where it's 0 or 1, which is discrete, right? 0 or 1, discrete, the expected value, okay? The expected value is 0.5. And I wrote here how. So it'll be what? 0 times plus 1 times, all right? That's it, right? Because we have the probabilities and the values. So that's how you get 0.5. And for the continuous part, remember, for x values between 0 and 1, we have this thing here. So continuous part, you can take xfx, integrate from 0 to 1, and you'll get 2 over 3. Okay, so this is for the continuous part. This is for the discrete part. So we know that x is a mixture. Remember the word, yeah? I told you about it, right? So the expected value of x will be this thing here. What's the chance of this happening? Good, 10%. This thing here, what's the chance of this happening? If it's 10%, this must be 90%. That's it. So rather than tell you about formulas and all those things, right? Just the idea. First, you work this out, 0.5 and 203. And what's the chance of this happening? 10%. There you go. And what's the chance of this happening? 90%. And you get your answers. Okay, that's the expected value of x. But look, that's not what they want, yeah? They want the variance. So you need to go and work this out. The second moments of your discrete part. Excuse me, let me just move this up. Okay, now we work out the second moments. The discrete part won't have any change, right? It will not have any change. Okay, go and do it yourself, right? It's pretty straightforward, right? Okay, because of the fact that we have got, let me write it here again, right? X equals to 0, probably x equals to 1. Both are what? 0.5, right? So the second moments will also be 0.5. 1 squared, right? Times 0.5 is 0.5. And this one, you need to do a little bit of work, okay? The density function is 2x. So you want x squared. So it'll be x squared times 2x. You'll get this. Integrate from 0 to 1. You'll get a half. Same way, what are the chances of getting 0.5? Good, 0.1. What are the chances of getting a half? 90%. So use a calculator. You'll get the second moments of x, expected value of x squared, as 0.5. Variance, now it's easy, right? 0.5 minus this one here, 0.65 squared, you will get a nice number here. Okay, so this idea of mixed distributions also works for moment generating functions. You can go ahead and look up. This is found in many books, right? It's not something unique. It also works for mixed distribution, right? So I repeat, let me say it again. Here, y is a mixed distribution. This idea that we just talked about here, maybe I mentioned this before. We have used C1 and C2, I think, in our previous videos. So when you are dealing with a mixed distribution, this idea works for moment generating functions as well. Okay, but works for moment generating functions as well. So if C1 mx1t plus C2 mx2t.